Okay, this section we will talk about the how to select the drive, part A. Talking about the process adjustment. Before we use the drive, there are several ways to adjust the process. For example, adjust the flow of the in the pipe. The first way is throttling. You change the angle, of the throttle. The second one is bypass control. And also you can have the on and off control. And if we use the drive, then you have the much easier way. Because before you use the drive, the speed of the motor is fixed. Now you can adjust the speed of the motor by the drive to adjust the flow. And you can have a very accurate control of the process and also have continuously adjust the process flow and also energy saving because you change the throttling, a lot of energy is wasted on the damper on the throttling. And after you use the drive, the valve will always 100% open. So there is no loss on the damping. Talking about the two quadrant and the four quadrant, this is a typical low volt drive. Use the diode rectifier, convert S to DC, and then you convert from DC to AC. So because the diode is on only one directional conductor, current cannot go this direction. So that means the power of the drive cannot feed back to the grid. So this drive can only run at the full quadrant. If we look as we talked before, speed and torque, only this 1 and 3, only this two quadrant. You cannot, because quadrant 1 and quadrant 3, the power is always plus. So this drive is only two quadrant, no regeneration function. If we want the drive to run with the full quadrant, power regeneration, we need to use this kind of topology. The rectifier, we use IGBT rectifier instead of the diode rectifier. Then, if there is energy regenerated back from the motor, here's the inverter, right? Here's the motor. If the energy back from the motor inverter, then to the DC, we can regeneration and backfeed to the grid. So this is a full quadrant drive. Talking about the single drive and multiple drive. This is a typical single drive. AC input, AC to DC, DC to AC, and one motor, one drive, one motor. Multiple drive means, multiple motors with a multiple inverter, but with a common DC bus. This is called a common DC bus. The DC bus of different drive, is parallel, connected together, and with a centralized converter, AC to DC is centralized, and DC to AC is distributed. We can have several. Advantage of this kind of topologies, for example, this motor have a regeneration of the power, mechanical power to electrical, and then back to the DC, and most of the energy can be absorbed of the other drives if the other drives are running in the motor condition. So you don't need to backfeed to the grid. So that means the size of the rectifier can be minimized, and because a lot of the braking energy go to the other drives, cannot go to the grid. So the efficiency is also maximized. The power loss is minimized. So this is a typical multi-drive. This is the input grid side, and we have the input cabinet and the filter, IGBT converter or diode rectifier, and the different inverter with different motors. And sometimes we will have a chopper. This chopper is to control the DC voltage. In case of DC voltage exceeds the certain level, and the chopper will work and absorb the energy to the resistor to dissipate the energy on the resistor. Make sure the DC voltage will not exceed the limit. And here is the control. And this is a typical multi-drive, the outlook of the cabinet. This is by our company, Namco. And this is the inside of the cabinet. We have the input cabinet, rectifier and filter, and a different inverter. And talking about the gearbox, and most of gearbox to reduce the speed, and sometimes they also used to increase the speed. So here's the motor, and the motor initial. Here's the gearbox, and the load, and the load initial. Then direction of the energy, mechanical energy from motor, and transferred to the load. And then we have several formula. This one, motor power on the shifter, P1 here, P2 here after the gearbox. So the efficiency is decided by the loss of the gearbox. If there is no loss, then P1 is equal to P2. Then we get this formula, because P is equal to T and N. And we also have K. If this is omega, and then will be like this. So the relationship between prime torque and the second torque is like this. And also the formula for the initial. The load side initial, if we convert to the primary side, you need to get this coefficient. And we have different types of load. This is speed, torque. This we call the quadric. Quadric load torque proportional to the speed square. And because P is K1, is K2 torque and speed. So P is proportional to speed, cubic of speed. So this is torque, power. This is a constant speed, because P is proportional to speed and torque. So constant torque, then P is proportional to speed. So torque is like this, P is like this. This is speed, this is torque. Okay, so constant power, as we discussed the last time, power will be constant and torque will be reduced, because torque is K plus B N. And this is the constant torque with high starting torque for some of the special load, like the Mio, because they have a friction torque. So in the low speed, they will have a high torque than the normal. And also this one is below the simple speed, you have a constant torque. And above the single speed, you have the constant power. So this kind of a combination for constant torque and constant power. So for drive, the ideal curve will be like this: speed, torque, constant power. But the real situation, the torque will be reduced with the speed. Partially because of the limitation of the VFD, the control performance of VFD, and mainly because of the motor. Because we know, that the motor, this is the load of the motor, and for most of the motors, cooling is by a fan on the shaft of the motor with the coaxial. So in that case, when you reduce the speed, the airflow reduced, then the ventilation reduced, the motor will be heated with the high torque. So the actual torque should be reduced to make sure the motor will be not overheated. So if we convert this fan, cannot mount the fan on the shaft, we drive the fan with a separate motor and an independent motor. and the motor speed is always 50 hertz, always with enough flow ventilation. Then we can get the relatively ideal constant torque. Okay, this is all for today's section. Thank you. Bye bye.